So could you please tell us about yourself?
Yeah, so I'm Huang from Penn State Aerospace Engineering. Now I'm currently an assistant professor there. I have been there for about 2 years. And I joined Penn State in 2019. Prior to that, I was in University of Michigan, had my PhD there in aerospace engineering. Yeah, and that's my basic information.
So why did you want to become an aerospace engineer?
Yeah, so that's then traces back to my high school. That's when I really liked the math and physics, and also get the chance to be exposed to numerical computations. And then, so when it comes to choice of major, then, well, I did my undergrad in China, and there's this major called aircraft design and engineering. And that's something that sounds like there's a lot of math, a lot of physics, and I will be building something cool, like a mechanical thing that flies, right? So I think I'll just choose that major. Yeah, and then it turns out, yeah, indeed, it's really cool. So I really like it, right? And then furthermore, I then wanted to continue on this path, and then that's why I came here to do the PhD and then continue on as an assistant professor, which that way I can chase some of my specific things that I'm interested in aerospace engineering.
Mhm.
Okay.
So can you talk about how you do fluid thermal structure interactions modeling and its importance in aerospace engineering?
Yes, right. So then we'll then round in some ways, like starting from hypersonic vehicles. That's what I did for my PhD and also what I'm doing now for my research. So for hypersonic vehicle, I guess you have the rough idea, right? Flying faster than at least a Mach 5, right? And then at this speed, the air is passing through the vehicle so fast, so that it's creating a strong friction, heating effect on the aircraft. And this is totally different from the conventional aircraft, like the one you take in the airport, or the one you see in museums with this F-22 or something. Those are like maybe at most Mark II, right? It's still supersonic. Now, at this very high speed, actually, this probably will relate to the other question: what is high temperature effect? That's a unique effect in hypersonic flow. So if you imagine that you heat up gas, what will happen? Like heat up to probably you won't see the oxygen or nitrogen anymore. You'll see atoms of oxygen, atoms of nitrogen, but totally not those molecules at all. Right? That will change the properties of the gas significantly. And this is a flow phenomenon that happens at a hypersonic flow. And that's something that the hypersonic vehicle needs to account for. Right? So that's why here we have this new field called fluid thermal structural interaction, or another word, aerothermal elasticity. It's a combination of three terms: aero, thermal, and elasticity that goes with the fluid thermal structural interaction. So those three, the two combinations of terms, they are essentially the same, right? Right. So then that's why we deal with this subject that accounts for the strong heating from the aerodynamics to the hypersonic vehicle, right? And then when we design this kind of vehicle, we do need to account for this effect, right? And then, but to give you a ancient example, like do you know the SR-71, the Blackbird?
Yes.
Yes, right. So then you probably know that when it's on the ground, the fuel will leak, right? Because when it's flying at Mach 3, the structure will heat up and expand. and then to avoid the leakage, avoid the structural buckling when it's flying, it has to design the structure such that it's leaky on the ground when it's not heated. Right? And that's only Mark 3. And now we are talking about a Mark 5 or Mark 6. The heating is even stronger. So that requires a actually totally different design methodology to account for those thermal effects. Right. So, and then that's why we study this aerothermoelastic behavior to design a vehicle actually can fly. Otherwise, it won't fly. Actually, it will just crash at the beginning, maybe.
Mm-hmm.
Yeah. So, yeah, and yeah, I think with this, I have covered your questions 3 to 7.
Mm-hmm.
Yeah.
So you do research about structural dynamics and adaptive structures. So what are some of the adaptive structures concepts that you're currently working on?
Well, so first of all, when we talk about FTSI, there is a fluid and a structure interaction, right? So that is structural dynamics.
No, okay.
So yeah, so that's why why I also say I'm a structural dynamic because that's how the structure vibrates, and it's not vibrating in just any simple manner. It's influenced by the airflow, and the structure also influences the airflow. Right? There's an interaction. There's a feedback between the two domains, the structure and the fluid. And for adaptive structure, well, I don't know, do you do edits to the video? Because this is not really what we do. I mean, you saw that on the website, but that information is kind of outdated and inaccurate. Yeah, but besides all those, I think I'll just add one more thing that's not in your set of questions.
Mm-hmm.
That's about how I use this machine learning approach to help accelerate my research. Right, so do you have some understanding of machine learning?
Do I have what?
Some understanding about machine learning?
No, I don't.
Oh, I see. Yeah, so this is more about so far you probably have mainly learned about these science or physics that are based on equations, like Newton's law or something, right? It's just an equation, and these are what people try to observe from their experiments, right? They have data, and then they have derived this formula based on those data by human. Right, but then machine learning is essentially saying that we use a computer to learn some kind of function from the data instead of letting the human learn that. We let the machine do that, and then that's kind of easier for nowadays for the like when we do real engineering, because we have so many data sets and they are so complex. It's really not much possible to have the human to look through those data and then derive something analytically. And we have to let the machine do that, because as you know, the machine, computers, they are good at doing these tedious numerical computations. Right, so we let the computer to learn that model. And then this way we can use this data-driven model to describe the physical process that we are interested in. And then this can be used to replace some of the unknown components in my analysis for the hypersonic vehicle. Mm-hmm. Right, so that's another important thing that I think I'm doing. Applying these techniques to, for example, the analysis of the flow near a ship, where the flow is quite complex. And if you imagine you are piloting a helicopter going to land on the ship, that complex flow will kind of interact with the helicopter. I'm not sure if you have seen some short videos on helicopters kind of trying to land, but due to the gust, it kind of fell off the desk, right? It will fell into the sea. So that's again something that's very important to understand. And my machine learning methods are helping this kind of analysis and engineering. Okay.
All right.
Yeah.
So what would you say has been your toughest accomplishment so far in your career?
Yeah, I would always say my toughest accomplishment is always my next accomplishment. So, right then I guess my toughest one would be my current thing that I'm trying to do, and these are something again. Well, it's more like some technical details, right, on how I really apply these methods that I described just now to solve the actual engineering problems. But I always aim for harder problems. And that's why I say the toughest thing will come next, always.
Mhm. All right. And what is a big milestone that you're looking forward to in your research?
Yeah, right then that will be a little bit, might need a little bit background, right? So for computational research, you probably don't know linear algebra. Do you know linear algebra?
Do I know about
Linear algebra.
Artuboro?
Linear algebra.
Oh, yes, I do. I do.
Oh, you do? Okay, that's great. So you know how to solve linear systems of equations, right?
Mhm.
Right, and then you probably have an idea that the more equations you have, the harder it will be to solve, right?
Mhm.
Right, and then if we think about there are n variables in the equation, and then the cost is actually proportional to the number of variables,
Mhm.
right? And actually, to be more accurate, it's proportional to about the cubic of the number of variables, right? And then, although there are some advanced algorithms that can drive that to be a square of the number of variables. Now, the thing here is that for modern engineering systems, when we analyze these systems, the n can be millions or billions, right? And then the cost for solving these problems, it at least squared. So it's a billion squared. Well, what's the number then? It's much bigger than trillions, right?
Mhm.
So this is a crazily high computing cost. That's in sometimes it's impossible, right? And then my work is essentially trying to reduce those unknowns or number of variables to something maybe like 10, right? Initially from a million variables to 10 variables. And then we can solve the problem really easily, right? And then this has been done for some simpler problems. But then what I would call the holy grail in this field is then for any problem, we can do this reduction. And then that way, we would be able to do any engineering analysis in a very efficient way, and then solve or design many cool aircrafts or whatever,
Mhm.
right? So that would be my milestone, although this might be still a little far away. So, but that's my goal.
Mhm.
Yeah.
And to high schoolers like me and to younger generations that want to become aerospace engineers, what would your advice be to be successful in this career?
Yeah, so I would say two things. One is you do need to have a very solid basis uh, on your math and physics. I mean, these STEM type of capabilities, right? Because the things do look really cool, but if you want to work with those, you do need a very strong understanding of what it is doing. And to understand those, you do need a very strong mathematical and physical knowledge on that. That's one thing. And the other is always the passion uh, for whatever you're doing. right? Many times it's not the knowledge that you are lacking that prevented you from finishing a deal. It's more like just somehow the passion just is worn out, and then you don't want to continue, right? But it's always have that motivation or that enthusiasm to go through the aerospace applications. Right. So that would be the two things I have for the high schoolers.
Mhm. All right. Well, thank you for joining me, and thank you for letting me interview you. And I think that was great.
Okay, sounds great. Then do we just